We take for granted using computers every day, and we even get frustrated when they don't even work the way we want them to. But no one really knows the underlying complexity behind computers, and even when they don't work, they're performing billions of calculations in a single second. Today, I want to show y'all a glimpse of how a computer works in this basic simulation. But this is only a glimpse, only a taste of what a modern marvel of a computer that we use today can even perform. And all the calculations that our computer will perform, a modern computer can perform in a nanosecond. But please enjoy the rest of this 3-hour video as I describe in full detail, like never seen before, about how a computer works on such a fundamental level. So welcome back into the simulation, and this is going to be a little bit of a different video, as you can tell, because I have this green screen up right here and I'm actually going to be in the simulation. But also look at the timestamp on this video, and it's 3 hours. It's probably more than 3 hours, probably 4 hours. This is a full in-depth guide of how to build a 8-bit computer, and the other video I did was 1 hour, but it wasn't really a full computer. This one can be a full CPU and a full GPU, just like they would make in the 1970s. So that's what we're going to replicate in this video, and I'm going to show every step made, every single step. I recorded it. It's 4 hours long. You're going to see all the mistakes I made and all the problems I had to go through in order to fully make this. But if you're impatient and you do not want to watch this video, understandable, it's 4 hours. You can go to my shop in the description below. And if you want to, you can buy the CPU right now and you can load it into your digital logic simulation so you can play around with it and see what kind of cool stuff you can make with this simulation. But that's going to be in my shop below. If you want to make it yourself, just watch this video and just copy all my moves, and then you will make the CPU yourself. But again, if you just want to kind of play around with it, or you want to buy it and then tweak it, make it better, you can. This CPU does work, and it's actually a lot better than the 8-bit CPU series that we made, but it's still not perfect. There's a few things that I would like to fix, but I really didn't want to think about it too hard or too complicated to fix it. So I have a solution that works, but the GPU is slightly inefficient, but the CPU is pretty efficient. So let's just start with the video right now. So before we begin this series of how computers work, I'm going to explain how the simulation works, how to download the simulation and whatnot, so you can get started if you're essentially starting from scratch about how this computer works. So this simulation that we use is called Sebastian Lague DLS, which stands for Digital Logic Simulation. Put a link in the description. It's very easy. All you got to do is look up Sebastian Lague Digital Logic Simulation, and we're using the May 2025 version of this because there really hasn't been updates after. There is a community edition, and I'm aware of it. I haven't really fooled around with it, but I heard it's better. But I'm just more familiar with this platform right here, so we're just going to use this one for this video. So let's start off with basics of computers, and that is computers operate in ones and zeros, if you haven't known. So it can either send a signal that's high or a signal that's low. There's also kind of this third signal that we'll talk about later with tri-state buffers, but I just want you to kind of put them in the back of your mind right now. So data can be stored like this, and so we have to use a base 2 system. And we use a base 2 system because we have 2 inputs, on or off. So a base 2 system multiplies kind of the next digit by 2. It's 2 exponentially. So we use a base 10 system. So each digit after 1 is essentially multiplied by a factor of 10. But in a base 2 system, it's multiplied by a factor of 2. So a 4-bit binary number will have a 1 spot, then a 2 spot, because 1 times 2 is 2. 2 times 2 is 4, so we have a 4 spot. And then 4 times 2 is 8, so we have an 8 spot. So that's how we represent numbers in binary. And then 4 bits is called a nibble. 8 bits is called a byte. I forgot, I think it's 8 bytes is called a word. And then so on. So that in computers, pretty much everything's on a base 8 system. So you have an 8-bit architecture, 16-bit architecture, 32-bit architecture, all multiples of 8. That's essentially the essentials really you need to know about how computers work, and we can manipulate the bits using these basic logic gates that we're about to make. So let's talk about how the simulation works real quick. So you're starting out with just the NAND gate in the simulation, and that's just a single gate at the bottom. If you look to the left, we have these inputs right here. So we can either have a single input, a 4-bit input, a nibble, or an 8-bit input, a byte. And then if we go to the menu, there's actually some already pre-programmed computer architecture stuff that we can use, which you can see is a tri-state buffer, a bus, converters, so we can convert nibbles to bytes, and we can convert single bits into bytes. And the converters really just allow us to wire everything up a lot more smoother. They don't do any logic by themselves. They just allow us to wire things up very smoothly like this. And then we can draw wires by clicking and drawing. And if we want multiple inputs at the same time, we hold down the shift button. So if you see me like spawn in multiple like gates at the same time, multiple inputs at the same time, it's because I'm holding the shift button and clicking them. And then you can spawn in multiple gates at the same time. And so you'll see me go to the menu also multiple times and use some of the pre-programmed gates and devices that they have. And then if we go to the preferences, we can control the clock speed or how fast our CPU is going to run at. And that will be talked about more in the future. But that's a basic layout of how this digital logic simulation works. Okay, so first things first, I'm going to look at my laptop right here as I do it. So if you see my eyes moving, that's because I want to see where I am in the video. And we had this NAND gate first. So NAND gate, 2 inputs, 1 output. But if you hook up the same input to the 2 inputs, you make a NOT gate, which is just an inverse of a normal gate. So the input is low, the output is high, and vice versa. I'm just shaping it to make it smaller. This can be pretty fast too if you can't tell. So NAND gate plus a NOT gate makes a normal AND gate. And an AND gate only turns on high if both the inputs on are high. And then the output will turn on high. And that's an AND gate right here. A NAND gate, if both the inputs are on, the output is off. And that's an AND gate. But the NAND gate's already pre-built into the simulation. And you can make a whole computer with just a NAND gate. So you take a NAND gate, take 2 NOT gates, put it for the inputs instead, and a NOT gate for the output. We're going to get I think it's an OR gate. Could be an OR gate. We're going to see what the simulation says in a second. It's an OR gate. So it's an OR gate. So if one of the inputs is on, the output is off. If both the inputs are off, the output is on. It's an OR gate. So we just remove the NOT and just hook up the NAND directly to it. We get an OR gate. So if either one of the inputs are on, the output becomes on. And that's just an OR gate. Now for a fun chip we're about to make, which is the XOR gate. It should be. Okay, yeah, it is the XOR gate. So it takes 4 NAND gates, you put them in this configuration right here, and if both the inputs are the same, the output is off. It's off. So if both the inputs are on, the output is off. If both the inputs are off, the output is off. But if either one is on, then the output is on. And then you can make an XNOR gate, which will turn on if both the inputs are the same. And you just swap out the NAND with an AND. So if both the inputs are off, the output is on. Both the inputs are on, the output is on. But if only one of them is on, the output is off. So we're only 2 minutes into this too, by the way. So now we're going to make something called an adder. So an adder or a half adder is just an AND gate and an XOR gate. And we're going to hook it up in this configuration. And this is how CPUs add numbers together. This is one of the most crucial things in a CPU. So apparently I did not like that design. Well, first of all, I'm going to show you all, I guess, all the logic gates that we have, which this is it right here. So we have the NAND, the NOT, the AND, the NOR, OR, XOR, and XNOR. So now I'm going to show you what really each of them do with this little simulation right here. I know I kind of I made the video footage for this before making the green screen footage, so I'm kind of seeing this too and seeing what I'm doing. But this is what Dom in the past wanted to do, so this is what we're gonna do. So just figuring out with the little settings a little bit, and then we're gonna go and see what each of these gates do in real time. Okay, so it's all hooked up right now. So if you see one of the inputs on, you can see how each of the different gates respond to that input device. And then we're going to see if both of the inputs are on and both of the inputs are off. And you can see how they're all responding differently. So you can take a second to pause the video if you really want to understand how each of these gates work, but they're pretty straightforward, I think, from their names. Okay, so now let's go and actually make the half adder that we were talking about earlier. So take an and take an XOR gate and take these two inputs. So we're going to hook up both of the inputs to each one of the inputs on the gates, and then the outputs to the output on the gate. So just like this. So if both of the inputs are on, the AND gate's going to be on, and if one of the inputs are on, then the XOR gate's going to be on. But like how a normal XOR gate works, if both of them are on, the output is going to be off. And so this is how you make a half adder. And I'm just rearranging it now so we have the carry output on the top, which will just make it kind of easier to wire in the future. So essentially we're saying 1 plus 1 is 2. That's kind of essentially what this says right here. So A is 1, B is 1, so 1 plus 1 is 2, and then 2 in binary is 1, 0, which is the outputs. So if you take two half adders and an OR gate, you can make a full adder, which can add 3 numbers up. And then we use the third bit as a carry input from the previous half adder, and which you'll see when we make our ALU, our arithmetic logic unit. With 8 bits, we got to carry, we got to ripple them kind of through each other. But this is the full adder right here. And yep, it works good, so we're going to call it full adder after I name all the pins. And you can use a full adder for subtraction too, with the carry input also. Or the C input, that's what I meant, C input, full adder, FA. So new chip, we're going to make a 8-bit adder, which we're going to take 8 of these full adders and kind of ripple them and chain them up together in order to make this full adder. So the overflow pin is going to be the last carry output pin is going to be connected to that one. So if the number we're trying to add is over 8 bits, then we're going to overflow it into the overflow pin. And that's essentially what we're going to do. And there's a way where you can use that. So an 8-bit computer can add up numbers that are more than 8 bits in width. And that's with the overflow pin. But our little computer right now, I'm sure there's a way to do that with the software for the computer, but that's kind of probably a little hard. And this is not a software engineering channel. This is an electrical engineering channel. So we're not really going to dive too deep into the software behind a computer, just the hardware. But right now I'm just wiring up input B and input A into the half adders like this. Yeah, I screwed up a little bit right here, so I gotta rewire it. I kind of miss an adder. Okay, so now they're all wired up. So now we gotta chain these full adders together. So you take the carry input and feed it into that C input, or that the carry output, and feed it into the next full adder's carry input, excuse me. And kind of just like this, kind of just snaking it along, so they all act as one like coherent unit in a sense. Now we got to feed all the outputs together into an 8-bit output. And the way the simulation works, you can make an 8-bit output kind of conveniently. So that's what this big black box is. It's just a converter. It just converts these single wires into an 8-bit output. And so that's essentially it for the adder. But of course, you got to add the inputs and the outputs. So 2 inputs, one's going to be A, one's going to be B. And then we're going to have 1 output. So, yep, this thing can add. So that's why we call it the add module. It's an 8-bit adder too, so we're going to have that little 8 so we don't get confused in the future. So it's an 8-bit adder. So now we're going to take our... I'm deciding. Okay, so now we're going to make an 8-bit AND unit. So we can do, our ALU can do more functions than just add. So we're going to add this 8-bit AND. Once I realize what I'm doing correctly, and I pick the correct unit. There we go. There we go. Okay, so we need our converters again to convert from 8-bit into single pin so we can make our module correctly. Okay, so the AND module is essentially almost created. So now we have this 8-bit AND module. And I'm just going to erase it, and then we're going to do the same thing with ORs. We want an 8-bit OR module, and then we're going to want an 8-bit XOR module. So now I'm just going to wire them up and feed them to the output. So Okay, so now we're going to make an 8-bit NOT arrangement with the NOT gates, so we can get a full array of all the gates that we have for our ALU, our arithmetic logic unit. So computers, if you don't know, are really good at math. And the reason they're really good at math is because they have a math unit called the ALU. And we're making the components for our ALU right now. So we can make it very shortly, actually. And this is the most essential part of any computer. It's computers have to be able to execute or fetch, decode, execute, and this is the execute part of the computer. So it's executing. So right now we're making something called a tri-state buffer, an 8 tri-state buffer. So we're using something already pre-built into the simulation, and a tri-state buffer is very interesting because normal gates, the output is either on or off. A tri-state buffer has a third output it can do, and that's neither. So it can be on, off, or neither. And that allows us to feed outputs onto the same inputs of the same devices. So let's say we have 2 ALUs and they're both feeding an ALU to a monitor or to an output device. We have to put a tri-state buffer after each ALU so they're both not trying to write data to the same monitor at the same time. So one of the ALUs is going to be in the high impedance category, which is neither. So it's going to output neither's 1 or 0. It's going to output nothing. And the other one's going to output as data. So that's what a tri-state buffer is really used for. And you're going to see its application in our CPU as we make it. But we need an enable pin. And if the enable pin is high, and that's the pin at the bottom of the screen right here, if that's high, that means we want this tri-state buffer to be on so it can write data to whatever we want to write data to, which most of the time it's a bus. And a bus is just a spot where multiple components of a CPU write data to. You can see if the enable is high, it sends its data out, outwards. And you can see it's representing the simulation with a dark black from a gray. So gray means 0, dark black means neither. So now we have our add, our 8 and, our 8 or, and then our 8 XOR. And this configuration right here is closely together as possible to make it neat. And man, what else does that look like? Or 8 not. But we're gonna configure it a little bit differently. Yep. Okay, we moved the not to the side. I knew we were gonna do that. So you need this tri-state buffer right here because we're gonna be writing this data. We have these 4 outputs and we want to write it into one single output. So we need these tri-state buffers in order to do it because you can't write multiple data to the same output, only one at a time. Because we're not a quantum computer. It's a classical computer. I want to move it a little bit down. I guess it was kind of bothering me where it was. Okay, now we're going to the library. We're going to get something called a bus. If I can figure out, okay, there it is. And a bus allows us to write data from different sources to the same source. So as you can see, the output of all the tri-state buffers is going to the same source, which is the NOT gate, which goes to another tri-state buffer. And they're going to write their data out to another bus, like this. So now we need some inputs for our ALU. So these are our 2 inputs. Remember input A, and input B, like this. And now we're going to have these 2 buses to connect the inputs all together. So I hope this makes sense, but for inputs, you don't need a tri-state buffer to differentiate what inputs go to which machine, because each of the components, the add, the and, the or, and the XOR, can all take in the data from the same from a similar input source like this. They can all take it in without any confusion happening. They just can't be writing data to the same source at the same time, but they can take in data from the same source at the same time. Now we have this 8-bit pin at the bottom, and this is going to be our control unit. So we have to be able to make our ALU know whether we want to, do we want to add numbers? Do we want to AND the numbers together, or the numbers together, XOR the numbers together, or do we want to not do we want to not enable the not pin? Do we want to disable the not pin? And so on. And that's our carry input, because we do kind of want that, so we can add numbers that are bigger than 8 bytes, and we need the carry input for subtraction if you want to do subtraction in the future, in which we do. So now we're just wiring the rest of these tri-state buffers up to our control unit, so we can control which one's on at which time, so we can enable different parts of our CPU to do different operations at certain times. And that's essentially what we're doing here. And I'm thinking right now, I guess, because I don't know what to do next. But I do know what I will be doing next. And it looks like I don't know yet. Oh, excuse me. Okay, so now we're making something called the zero flag. So if the number the ALU is outputting is a 0, we want our thing to be off. In other words, it not be outputting anything. And if and this is going to allow us to have conditional jumping, so we can know if two numbers are the same, we can know that the 0 pin will be on, and we can jump. So that's essentially what we want to do. And different computers have different stuff. So some computers have the OR gate as a conditional jump, and some have a NOR gate, so it's on if it's 0. In which we will be changing this to NOR in the future, because we want that pin to be on if it's 0. So we know that these numbers are the same. But this is our 8-bit LU in its final glory form. So now we're going to add one last thing to our 8-bit LU, and which this is really just for convenience. It really isn't too necessary for a standard LU, and that's a multiplier and a divider by 2. So if you shift the bits up by 1 unit or down by 1 unit, you're essentially multiplying the number by 2 or dividing it by 2, since binary is a base 2 system. So you'll look right here, we're converting all these to ones, and then we're going to output the data onto our thing. We're going to try to say buffer it first, though. And it doesn't matter if it's the input or the output for this scenario, because if it will still be outputting a high impedance either way. So we're just going to put it for the input for this because we just have a little bit more room. But I want you to watch closely as I wire this. So This top one's going to be our multiplier. So you can see that the bottom pin is actually becoming the second pin on the output. So we're multiplying it by 2. And then it's reverse on the divider. The top pin becomes the second top pin on the output, so we're dividing it by 2. And this is a quick way for us to do quick math if we really need to shift the numbers quickly in our simulation. But this is essentially it. This is our full 8-bit ALU chip. Okay, so the next thing our computer should do is be able to store data. And we can do this using different storage devices. And this is called an SR latch, which stands for set, reset. So essentially we can set the data to be on, or we can reset the data to be off. And I want you to look at this. Notice how one of the outputs feeds back into the inputs of our SR latch. And this is how we do it. And there's different ways to make an SR latch, but we're choosing this way because every time we reset the simulation, the natural state is going to be off. It's always going to be in the off state first round. You can make one with these 2 NOR gates like this, which is actually a more simpler design. But every time you reset the simulation, or every time you close out the simulation and reopen it, it's going to store the output in a random state, which we don't want that. We want everything to be stored as a 0 every time we reset the simulation. And this is going to allow for easier coding and easier debugging in the future. But they essentially work the same. So set, reset, we can store data. We're going to save it in SR latch. So we take 2 ANDs and SR latch, we put them in this configuration right here with an output. We get something called a D latch, which stands for data latch. So instead of set and reset, we can just save whatever data is being inputted into our input device, or our input side. So we're going to have a data input and then a save input. And we need these AND gates in order to kind of control the data flow. So S will stand for save, and then data will stand for the data, whatever the data is. So as you can see, it can save the data, and then once we press save, it will save whatever the new data is. So this is our data latch, essentially. So now if we kind of configure this a little bit to where we have these 2 data latches, as you can kind of see, together, we can make something called a flip-flop, in which it kind of changes its data depending on previous data. And you'll see this in a second. So the save state now is this NOT gate, so we can inverse its signal. And the same with the SR latch. So we have these 2 data latches with this NOT gate, so we can kind of inverse the signal. So notice too that if the save state is on and we change the data, the output will not change. We have to reclock the save state in order to make changes to the output. And I'm just switching out the NOT gate now, the NOT sides at least, as you can see. So we can so the data will save when the clock signal rises. So when the clock signal goes from 0 to high, it will save instead of going from high to low. So on a rising clock edge, the data will change, and the clock stays high, the data will not change. So this is going to be our D flip-flop. This is a data flip-flop. And this is going to be essential for how we store data. So now we're going to make something called a JK flip-flop and not a data flip-flop. And a JK flip-flop is slightly different. So if J and K, these inputs are both high, the output's going to alternate its state. So if the output is on, and then and J and K are both high, and the clock signal rises, it's going to switch from high to low. And if the output is low, it's going to switch from low to high, and vice versa like that. And then if J is on, it's going to say the output is on, and if K is on, it's going to say the output is off, essentially. Or I might have had that switched up or a little confused, but it's going to be either one or the other. So it's pretty basic. But that's essentially how this works. So we need 2 more AND gates for the J and Ks, and we're going to do something kind of interesting. At least I think it's interesting. So we're going to take the output of our JK flip-flop, and we got to feed it back in as an input. So it knows, hey, like, is the output on or is the output off? And then depending on what it is, it can flip its state in the correct way. But notice I've actually made it backwards. So the not signal is supposed to go to the J in this scenario, and then the not inverted signal is supposed to go to the K. So now when we clock it high, you see it alternates its states. So this is a JK flip-flop. So now if we remove the J and the K, which hopefully I do in a second, and we just put the outputs connected directly to the first AND gates, we can get something called a T flip-flop, which will just, no matter what, it will always alternate its state. And we don't need those 2 inputs. And this is essentially a simplified JK flip-flop with less capabilities, but it will save us kind of space in the simulation if we don't need the J and the K ability, if we just want to flip-flop its states. So we call this a T flip-flop, a toggle flip-flop. So now, if you can't tell, we take 8 of these data flip-flops, we put them all together into a single chip, and that will give us something called a register. A register allows the CPU to store data very quickly inside of it. So have you ever heard of CPU cache? That is how much data the CPU itself can store, and it's used with registers, and this is what a register is. So this can save an 8-bit number into a single cell. And that's what we're making. And we're using data flip-flops in order to make this. This is not how RAM works, and this is not actually how like SSDs work and storage devices work, because this is volatile memory. So once we cut the power from the data flip-flops, it will forget essentially all the data that it had stored into it. So we need power for it to keep its memory. And then RAM is also volatile, but it uses capacitors and transistors and a combination of that to get this RAM effect, essentially. And we use capacitors and transistors because it shrinks down one of the data flip-flops from all of those logic gates to just a single transistor and a single capacitor, which saves a lot of space on a RAM chip, but it's slower. So we use this inside the CPU because it's much faster. So now we're going to make something called the program counter, which is how the computer knows what program it's on or what program it needs to fetch. And this is a very essential part of a CPU. So we're going to make this, you'll see, right now I'm just configuring the NOT gate because it's a little thick, and I don't like the thick gates. I like my stuff to be small. So we're using a smaller version of the NOT gate, and I just went and configured it real quick. So we have this small NOT gate and these 2 AND gates, okay? And we're going to have this OR gate at the end of it too. So we're making something called a multiplexer first in order to make our control unit. So a multiplexer allows us to pick what's if either input A or input B is to be outputted from the system. So it's kind of like a tri-state buffer in a sense, where if you have multiple inputs feeding into like a certain restricted area and you only want one of those inputs through, you can use tri-state buffers, or you can use a multiplexer. But some scenarios it's a little easier to use one over the other. And so that's why we're going to make this multiplexer real quick. It's an 8-bit one. Yeah, so like I'm really screwing this up how I'm making it right now. Just give me a second. So the input, as you can see, the single input that's connected to this 1 to 8-bit converter feeds into both of these AND gates with a NOT gate in between, as you can kind of see from this. So it's going to pick which AND gate is activated, so which data can be sent through, essentially. The simulation is kind of stalling right now. It's a little, it's glitching out right now. I'm just going to reset it real quick. This is our 8 multiplexer, like that, multiplexer mux. So I'm going to reset it real quick in order to make it start. I don't know why it's doing this. Okay, so it looks like it works now. Good. So you can see the NOT gate is outputting correctly, and there we go. So if we had arbitrary data in each of these, depending on if the enable button is high or low, depends on which one's going to be outputted. As you can see, it's alternating which signal gets outputted through the system. And this is our 8-bit multiplexer. So this is crucial for our program counter, as you'll see. So all we need is actually a whole bunch of half adders like this, a few converters to convert from 8-bit to a single bit for our half adders to work, like what I'm doing right now. We need some converters. And then we're just going to wire it up as normally, as hopefully you can kind of now expect, because you're gaining all this CPU knowledge. So outputs to outputs, we're using not the carry output, but the normal output, and we're hooking up these inputs together like this. And then we got to, hook up the carry to the previous one like this. So half adders, oddly enough, can add any number by 1, and that's really all they can do by themselves. That's perfect for a program counter, because if we want to go from program 10 to 11, we just got to add by 1. So that's all we got to do, which is how computers work. They follow instructions. They follow orders from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. They don't jump from like 1 to 5 to 8 to 15. They don't jump around like that usually. They normally go increment in order. And it works. So we can add numbers by 1, you see. So good. So this is our add 1 circuit. And now we're going to take our multiplexer, our add 1 circuit, and then our register, the register that we made. So if we hook it up like this, so the multiplexer's output is hooked up to the register, the add is hooked up to the multiplexer and to the one that's normally outputting, and then we hook up this 8-bit input into our multiplexer like this, we have our program counter, essentially. So in our we need output, of course. So every clock cycle, every time the clock gets pulsed to the multiplexer, we're going to increment it, the number by 1. But computers have this function where they can jump to different programs called biconditional jumping. So if you ever coded, and let's say you say, run this loop until x equals 3. So when x equals 3, the computer's 0 flag's going to light up and let the program counter know that, hey, we need to jump outside of this loop. We need to be done executing this loop. And that's essentially what our jump thing's going to do. So you can see every clock cycle, we add the number by 1. Okay? And if we want to jump, we just we press the jump button and then we hit the clock cycle and it's going to jump. And you can see our jump input is 0, 0. So it's jumping to 0, 0. But we can jump to any number we want to. And that's our program counter. So that allows this to be a turning complete computer. And that's the hard definition of a computer. It has to be turning complete. So that means it can execute any mathematical operation you want it to, given enough time. And it needs to be able to jump in order to do that. And that's exactly what we made. And that's exactly what we didn't do in the first video about how to make a computer. We didn't have the jumping feature. So now we have there's 4 essential things in a CPU. We have 3 of them made already, which is our ALU, so we can do arithmetic, our register, so we can save the data, and then our program counter. We need a control unit next, but we're going to worry about that a little bit later. Right now, we're kind of just making the skeleton of how our CPU is going to look like. So we have these 2 registers hooked up to our ALU. Those are called accumulator registers. We have accumulator register 1 and accumulator register 2. And then we're going to have these 3 other registers that we can just hold arbitrary data in, or data in that we need our CPU to like remember but not necessarily access immediately. So those are going to be called like our cache cells in a sense in a normal CPU. But we only have 3 bytes of cache. Normal CPUs have a few, like 64 megabytes of cache. So our computer is substantially worse than probably a calculator on your desk is. Actually 100% worse than a calculator on your desk. So we're going to kind of configure this in this way right here. You're going to see I'm going to remove these cache registers in a second in order to create a register, just to combine them in the one chip to make our CPU look a little prettier. But our program counter is going to be outputting its data from the CPU onto something called an address bus. And an address bus is going to go to our memory, so the memory module knows which address we want to access the code from. And then our accumulators are going to get fed data from this data bus, so we can save data to input into our ALU. And our ALU is going to also be outputting data onto the data bus, just like this. So this is our CPU. Now let's make the register or the cache cell, essentially, which is this going to be, we're going to have three main registers. So we have three tri-state buffers, three registers, because all these registers want to write to the same output, which is our data bus. So we need the tri-state buffers to determine which register gets the authority to write to our bus, essentially. So we're going to have a mini bus within our cache unit, you can say, our register bus, and that's what this is. And they're all going to have the same input too. And we'll be able to pick which register saves the data from the singular input. And that's what our control unit is going to be able to do. Our control unit is going to be able to read the code and then decide which modules in our CPU are activated depending on what that code says. So the control unit's almost the conductor of an orchestra, you can say, but we're not really there yet. We're still at the our cache cell, our register cell, whatever you want to call it. So I have these SR latches hooked up like this, and that's because these are tri-state buffers, because if they're activated, we want our register to continue to output its data for multiple clock cycles. So let's say the ALU needs to read its data, the GPU needs to read its data, and the program counter needs to read its data. So that's 3 clock cycles right there. And if it all needs to read its data, it can do that for multiple clock cycles. So we use this SR latch right here. So this one's going to be the reset. So it's going to unactivate all the SR latches. And then these are going to control which register cell is activated, has the authority to be activated by. And if we screw up our code and we activate multiple register cells at the same time, it's going to try to write too much data to a certain point at the same time and screw everything up. So what am I doing right here? Essentially, I'm just trying to make the control logic to control this register unit just an 8-bit logic unit like this, just so we can save space and not have a whole bunch of individual wires coming out of it and just one main 8-block wire set. But essentially it's going to do the same thing. So we can control which register saves the data from the data bus and which register is going to be able to write data to our data bus. And it looks like it all works. So, good. We're going to save this as a register cell, reg cell, just like this. And then we're going to plop that right into our CPU. So, man, I'm 45 minutes into filming this video. It's be a long video. Long video. It is 3 hours of footage. 4 hours. 4 hours of footage. So probably as we progress more into this video, I'm going to become more and more insane. I need the coffee to keep me awake. So, man, what am I doing? Okay, so now we are in the ALU right now, and we're going to do almost the same SR latch strategy that we did with our register cell. So let's say we want to add for multiple clock cycles. We can't do that right now with our current setup. So we need to add these SR latches in a similar array that we did to our register cell. So SR latches will be connected to each of these components, so we can add for multiple clock cycles, or we can AND for multiple clock cycles, XOR for multiple clock cycles, etc. And if we want to disable them all at once, we can with our little control unit that we have right here. So I'm just going to be wiring this up right now, and then we'll get back into our control unit logic, I think, next. And sadly, we have 9 inputs and only an 8-bit input thing. So we have to do this kind of weird little setup right here, where we can control which units on our ALU. Then we have to be able to discontrol it or disable it all. So there's our beautiful register cell, our cache cell, connected to the data bus. And we can't really do anything with that yet because we don't have a control unit. So I don't know what we're doing. I kind of just deleted that and just place it there. Like, what am I doing? We're gonna make these straight because we gotta have a good looking CPU. Like, come on, bro. So make all of these straight. Yeah, that looks really good. Fantastic detail to our CPU. Save it because, computer can glitch. We gotta save our progress. We did so much right here. Oh, new chip. What are we making now? What are we making? Take your guesses right now. That's right. It's a control unit. We're making the control unit. So if you got it right, give yourself a round of applause. So a control unit's basically a decoder. So what's a decoder? A decoder takes in a binary input and then makes it into individual outputs. So this is a basic 2-to-1 decoder. So we had this binary input, which is 2 bits, so it can represent 4 states. And then we're going to output each of those states as a single output. So it's a 2-to-4 decoder. And hopefully you can see what it looks like in this. Or maybe I just won't show at all how it works. Oh, I just won't show how it works, but you gotta trust me on this. So a 2-to-4 decoder takes in 2 binary inputs and makes these 4 outputs, right? So if we can take 2-to-4 decoders, we can kind of AND them up. I don't know, that was not right. So we can hook each of the outputs to its own separate AND gate like this. And then we can have this NOT gate to determine which AND gates should be activated, essentially. And then we can turn 2-to-4 decoders into one 3-to-8 decoder. What? Yeah, I know. So we can essentially have more outputs than what we originally had in the first place. So we need 3 of these. But the way that it's hooked up right now, I have to do a little bit of crisscrossing, which is not really cool. But we hook up the one spot to the one place on the 2 to 4 decoder, the same one, and the same thing with the top one too. And now we got to have 8 individual outputs. But we have to hook all of these up to our third input. So our third input's going to decide which AND gates are activated, so we can switch them. Yes, I made too many of these. So let's see. Do I give a little demonstration? I do. So look. So as you can see, we can control which output is on, and then if the third output is on, we can control which output is on from the top row. So this is our 3 to 8 decoder. So if we take 2 3 to 8 decoders, hook up the same AND bit array that we did earlier with our 2 to 4, we can make a 4 to 16 decoder. Crazy, huh? Crazy. So that's a 4-bit input, a nibble input, and that's what we're going to use for our 4 to 16-bit output. And essentially, we're doing the exact same thing that we did on our 3 to 8 decoder, except on a slightly larger scale. But I get kind of smart in this, and I'm going to use these 8-bit ANDs that we made earlier, so I can save up some wire space and some wire hassle. But it's still going to take a converter to kind of do it. So we gotta go get that 8-bit converter. That 8-bit converter. So that's what we do. Pop them down just like this. We need a few 8-bit converters, which is chill, big chill. So okay, so we converted them successfully. Good job. Then we're going to not this. So we got to hook this 1 to 8-bit converter up to everyone, so the 1-bit controls each individual 8-bit. And so we can decide which AND gate should be activated, essentially. So we take the bottom one. I don't know why, but I just inverse this. Hopefully I realize this soon that it's inverse. I just realized it. So that's kind of lit. The NOT gate should be in the bottom one because it should be normally active, and then the top one should be normally not active unless we want it to be active. So now we have these 2 outputs, and look at that. We can control which of our 16, which number it is being displayed. Beautiful, 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 beautiful. Oh man, so where were we? So now the 4 to 16, we get two 4 to 16s. Combine them together. Guess what we get? Yes, we get a 5 to 32-bit decoder, and that's going to be our final control unit decoder that we're going to use, because we're not going to have more than 32 controls for our CPU to actually perform. So we're not using AND gates anymore because we have a lot of inputs we really need to control. So now we're going to use tri-state buffers. And remember when I said you can use a multiplexer or tri-state buffers? Well, this is a perfect scenario where you can see that we can use either or. And we're going to use tri-state buffers right here to save on wiring, to make it look a little bit nicer. So we're going to need some converters. That's what we need. We need some converters. So 8-bit to 32. and then we're going to need some 1s to 4s so we can hook it up to our 16. Other way around. Oh man. So I mean, this is essentially what we're doing. We're just hooking up the same ones to the same things. It's basically just a big 2 to 4 bit converter, but we're just gonna do it with this. The NOT gate, at the bottom, so we can activate which one we want to be activated. The fifth bit's gonna decide if it's activated or not, and then we hook it up to the top bits like this. Essentially, that's it. This is it. This would be our whole 32-bit converter. So as you can see, we can pick a number between 0 and 31, and we can get an output for it, depending on what it is. So this is our 5 to 32 converter. So now we can make the control unit. So we have the 5 to 32-bit converter, right? And now we're going to hook this up on, depending on what the input number is, decides what thing in our CPU gets activated. So this is called opcodes and operands, but we're just worried about opcodes. Opcodes are what binary number corresponds to what action our CPU takes, and operands is what number the CPU is fooling with. So let's say the opcode 5 means to add. So if the opcode is 5 and the operand is 6, we're essentially saying add 6. And if, let's say, the opcode 7 means multiply, so if the opcode is 7 and the operand is 7, we're saying times 7, essentially multiply 7 by 7. So the operand's the number, the opcode is the instruction. And so the control unit really only fools with instructions, the opcodes. So I have an opcode sheet right here, and this is what the information displays. So depending on the number that determines what the CPU or what our control unit does. So if the number is whatever, it's going to do whatever. And that's essentially what we need to make right here. So I need to look at each component in our CPU and determine what I want each of them to do. And we want opcode 0 to correspond to nothing. So opcode 0 will always correspond to nothing with my computers, at least. So if there is no opcode being fed into the control unit, it doesn't mess with anything in our system. Okay, so yeah, now we're back into our thing. Just kind of fast forward a little bit through the slow parts, and then opcodes. Wait, opcodes 9 through 16 are going to be for the ALU. Opcodes 0 through 8 opcodes 0 through 7, and then 8 through 15 are going to be for the ALU. 0 through 7 is going to be for our register cells. And then 16 and so on is going to be just kind of random stuff our CPU also needs to be able to execute. So right now I'm making opcode 0 disable ALU, which this is a mistake on my part. I will fix this later in the video, but this is a mistake. So we will not actually be using this at all. I might not even put this in the final video, to be honest. Okay, so our control unit is now in our CPU. So we're gonna hook it up like this, and as you can see, the red cells go to the red cells in the control unit. The control unit also goes to the ALU, so we can control if the ALU is adding, subtracting, multiplying, whatever. And the same thing with which register cell is being is data being saved to and whatnot. So now we're going back into the control unit, and we're going to add, oh man, some very important controls right here, which are jump controls. So 16 and so on are going to have some jump features in it, which we need some converters. So these are our two inputs. And remember from our ALU, we had the 0 output, and then we had the overflow output. So that's actually going to feed back into our control unit. So we can write code that says that if the number is 0 or if the 0 pin is high, we want it to jump to a different part of the program. So if two numbers are equal, jump to a different part of the program. And that's why I also said that in the ALU, we have that OR array to where we can check if it's 0. That last gate should be a NOR gate. When I filmed the video, I accidentally made an OR gate. It should be a NOR gate. So please make that change if necessary. But everything else so far is correct. It also, though, yeah, everything else so far is pretty much correct. So we add these two up to the AND gate, so we can say that if the 0 is on and we have the jump, if 0 is on, jump, we want it to jump to a different program if it is 0. If not, we just want to kind of skip and just keep going as normal. And then of course we have to have a button or an opcode that's jump no matter what. So like no matter what, just jump to a different part of the program. And that's it. That's the opcode right here pretty much for our jump. We're gonna So let's go back in the CPU. So now we have this updated control unit right here with some updated abilities. So now we can hook up this jump feature to our control unit, to the control unit jump input, so we can jump depending on certain statements. Mm-hmm. And then, like I said, we're feeding the inputs, the outputs from our LU to the inputs of our control units. And we're going back into our control unit because we need more controls too. We need to be able to save our accumulator registers, those two registers that go into the LU. And that's what I noticed right here. So we have accumulator save 1, or accumulator save 2, and then accumulator save 1. And so that's going to be our next two opcodes. And I'm trying to make this organized, but it's going to turn into like a kind of a web soon. But that's it. Save that. Go back to our CPU. And it's a little messed up. We're going to fix that real quick because it's going to bother me if we don't fix it. And then we're going to hook up our new opcodes, or excuse me, our new control unit abilities to the functional part of the CPU. And that's just like this. So So now we're going to add something too real quick, which is our data input. So like I said, remember when I said operands? If we want to have an operand, that's what this is. This is our data input. So we can input data into our CPU for it to use. So we, of course, have to use a tristate buffer so multiple sources aren't trying to output data to the same bus. And then that means we need another opcode so we can control whether that tristate buffer is on or off, so we can orchestrate which thing in the CPU is sending data at what time. So I don't know when I'll be putting that opcode into the control unit, but it will happen. So yeah, so remember when I said that disable ALU part of our register cell? We got to take that out right now. We're going to take that out. We don't need it because we want opcode 0 to correspond to the CPU doing nothing. And right then we had opcode 0 corresponding to the CPU doing something, which was disabling the ALU, and we don't want that to happen. So now we have a new opcode which will be disable ALU, which is a thing that is not 0. So we just took that out of our register cell real quick. And we're going to hook that up directly to our ALU. And then for the tri-state buffer, let's see, we do it real quick. We have to add this SR gate right here so we control whether that tri-state buffer is on or whether that tri-state buffer is off. And then now let's go into the GPU. So this is how we're going to make the GPU, and this is my third attempt at making it. If you buy the product off my shop, you'll actually see my first attempt at making a GPU because it's going to be saved in here. But I'm going to explain how to make this new GPU. So the way the GPU is going to work is a pretty smart idea. We have these GPU register cells, which are essentially just a 8-bit register with a tri-state buffer because we're going to connect them all in a bus formation. But we have 9 of them because we're going to split our display up into 9 sections, or a 3x3 columns, like a tic-tac-toe chart in a sense. So if we want to display a character, it has to be in one of those 3 positions, and then the character will be like stored. The memories can be stored in each of these register cells. So the way it's going to work is our CPU is going to send data to our GPU on this data bus that we are making right now, and then our CPU is going to decide which GPU register it wants to save it in, and then depending on which one it wants to save it in corresponds to its position it's going to be displayed on our physical display. So that's essentially what we're doing right now. It's just a lot of wiring since we have to connect each of the save states to the GPU register. But the bad thing about this is that there's 9, and 9 is not a multiple of 2, so it's really inconvenient with how we have to set everything up because we need 9 inputs, and it's not a multiple of 2, so we can't make it into like a nice even 8-bit input type of thing. So right now we're just wiring this up, and this is all connected to the save element on each GPU register. Because the CPU is going to determine which GPU register cell it wants to save the data it's outputting to it. And so that's essentially how we're working right here. There's going to be an input data bus and then an output data bus. And the output data bus is going to be connected to our display, and the input data bus is connected to our CPU. And so just give me a second to wire all this up, and then we're going to go to the next part of the GPU. But I'm going to explain, I guess, I might as well right now, how it's going to work, essentially. So, the GPU needs to know when there's new data being stored in the register cell. And then it needs to know, A, what cell got the new data, when is there new data in it, and then we have to take that data and then convert it into an image format. So there's really 3 things we need to do. And really the image format's the most important part, but the other 2 parts are just help optimize it, because if it knows, hey, there's new data, we can kind of skip all the other ones that don't have new data. So this is how we're going to do it. So it's which one is on, this is our little thing. It's just a whole bunch of SR latches right here, and the SR latches are going to save the state of each of the register cells. So the SR latch is off. Also look at this. So this is a multiplexer right here. We made a 1-bit multiplexer. We already made the 8-bit multiplexer. So I did a little camera off work, and this right here is a 1 to 9 program counter, or 0 to 9 program counter. So essentially it's going to do is it's going to increment 0 through 9, and then once it hits 9, it's going to reset. And that's so it can work with our 9 outputs. So we have to hook up these SR latches to these AND gates like this, and then we're going to hook up the 0 to 9 to these AND gates too. So these SR latches, the main function of them is going to be to remember the state of each GPU cell. So if the SR latch is high, it means the cell received new data, and we want to keep it high so the GPU can know, hey, this cell got new data, let's go do something about that. And then we had the 0 to 9 incrementer that's ANDed with the SR latches, because the way our GPU works, it's going to check each cell individually. So it's going to start at cell 1 and be like, does cell 1 have new data? No. Does cell 2 have new data? No. Does cell 3 have new data? No. Does cell 4 have new data? And it's going to keep going around in these rows in a loop forever. And if cell 4 does have new data and it's on cell 4, it checks it. And then if it does have new data, the SR latch will be lit up and the AND gate will be lit up and data will be able to pass through it. So now we have to be able to reset the SR latch. And we need to be able to set each of them individually, because if multiple registers receive new data about the same time, we want to only reset the one that we've already written the data to the display to. So we're going to have to hook up this AND gate with our disable input, and we only want to disable the SR latch that the data has been written for. So that's why we use this AND gate, and then we're going to take the output of the first AND gates and feed it back into this input. So if, let's say, register 4 has new data, the AND gate will be lit up for register 4. And that's going to be lit up to this back AND gate right here. So whenever the disable pin goes high, it's only going to disable the SR latch for register 4, because that's going to signify the GPU read the signal that that register 4 had new data, and now we can kind of reset it and can be like, look out for any new data that comes into register 4, essentially. So I'm gonna say it again, I guess, real quick. If register 4 received the number 1, it's going to make the SR latch high, and then once the program counter points to that register, that AND gate's going to go high, and then once we write 1 on the display, we're going to disable that SR latch. That's a quick example. So now we need to make this OR gate configuration, and we're kind of just ORing all these AND gates together, because we need just a one output button that says, hey, one of the registers, at least one of the registers, has new data. Let's go into write new data mode, essentially. And so we're just ORing all of these up into one single pin. Oh man, but this GPU is a lot more optimized than the other one. So it took me a while also to make this. So we're just going to call this write GPU. So if it's on, we want to write to our display, essentially. So this is we're going to save this chip now, after we make the 9 outputs for these AND gates too. So we're just hooking each of these outputs up to the AND gates, and the AND gate will only be on if the program counter, the 0 to 9 cell on the SR latch cell, are both high through the AND gate. Remember that. So we're going to save this. This is called which one. This is an arbitrary name that I came up with. It's not actually a real thing you can call it. But essentially, it's kind of like a stack counter, you can say, because we're making each of the registers 1, and we're incrementing by 1 through the stack. So now we got to hook up the input of which one on to the GPUs. And the way we're doing that is we're hooking up to the save signal through that the CPU is going to send to the GPU to save it into the register. So if the which one module receives a save signal from the CPU, that's essentially saying that, hey, this register probably has new data in it. Let's do something about it. And so that's why we're hooking it up to the same line as the save signal to our GPU registers. And I'm just trying to wire it up to make it look nice, because it's hard to make it look nice since it's 9, and we can't really use an 8-bit data wire to convey its information without a whole bunch of decoders, and I don't want that. Oh man. And so So now we need a little converter right here. So we're going to convert the which one data into this 8-bit data. And that we're going to send it to one of the read-only memories. So if you see, we have 3 read-only memories. The one farthest to the left is going to signify where we want to jump to, and you'll see in the future. I kind of have to think about how to say it. Also right now too, so if the SR latch is on, we want to enable that GPU register to write its data on the bus. We want to be able to read that data. So this is what we're doing right here. We're just feeding this output to each of the enable pins on our GPU register so we can enable the data. And then, so back to the ROMs. So the 3 ROMs are one's gonna stand for where the program counter needs to jump to. One is gonna contain all the data for all the characters we want to write to our display. And the third one's gonna be used for pointing our GPU of where we want to display each character on the GPU cell. Like almost where on the grid do we want to display it? Because we have a grid display, and each dot on the display correlates to a number. So if let's say we want to print something in hole 1, we can. But if we want to print something in hole 8, we kind of just have to add 8 to 1, and it's going to print it in hole 8, essentially. So right now we're just hooking it all up to we're hooking the converter up to this so we can feed it into the read-only memory. Oh man. So we have this adder now. So this adder is going to be hooked up to this read-only memory, and it's going to be hooked up to the other read-only memory too, actually, and the program counter is going to feed into that. So this mechanism is actually the core mechanism for writing all the data. So the program counter is going to increment by 1 through a series of numbers to the read-only memory, which is going to decode that program counter's data into data for the display to read and to print out characters onto it. And then we're going to go through this adder so we can decide which place on the display we want to write this data. So the read-only memory, the one all the way on the right, needs to be able to read which register cell was on so we can correctly add the right numbers to our second read-only memory so we can write the data in the correct spots. So right here we just have the SR latches feeding into the thing, so the CPU can control whether we are refreshing it, whether we are just doing other stuff to the CPU too. And yeah, so this is our pins for our GPU to kind of work with. And so we had to add the little clock signal to our 0 to 9 counter, so we can, every clock cycle, it's going to increment by 1. But now we have to add just this little basic logic to it, so it only increments when we want it to increment. But when it's writing data to the display, we don't want it to increment anymore. We want it to halt it just for a little bit. So we're going to take this AND and this multiplexer and essentially use that in order to halt it correctly. And then this little NOT gate right here will only write data to our display when there's characters being pushed out onto it. So we had this SR latch right here, this AND gate right here, to the program counter. So the program counter is going to jump to the correct character at the correct time. And so we had this SR latch. This T flip-flop right here is not essential. You'll see me take it out in a second. So I'm just not even going to explain why I put it there. But the clock signal is going to the program counter and then to our dot display. Just like this. So we need these two pulses too in order to make everything work together. So if the right signal goes high, we want to pulse a save state to our program counter. Just pulse it real quickly. And then that's going to allow the jump button to be on for our program counter, so it can successfully jump to the correct place that we want to write character or read character data from our read-only memories. And then we're going to send this high signal to the switch multiplexer so we can turn off that 0 to 9 incrementer, essentially. And you'll see too, if there is new data, we want to allow the clock signal to be pushed into the program counter. So, but there isn't new data, we don't necessarily want that to keep running on forever. So the disable pin 2 on the which one it is needs a pulse signal, and it needs to come from that top 8 converter too. So once we're done writing the character, that top 8 converter is going to send a high signal, which is going to go through this pulse module right here, and it's going to turn off all of our essentially it's going to turn off our which one module it is, so we can keep searching for new data. But this is essentially the whole GPU. It's essentially made. So this is it. We're going to test out some data right now, and we're going to see the GPU write to it. And you're going to see me take out this T flip-flop in a second because it does cause a minor glitch. But it will work for the first time. So as you can see, when we pulse the clock multiple times, once it kind of reads through the memory slots, we are printing out the number 1. The number 1 is being printed, so it works. And this is the data in each of the ROM modules in case you want to replicate the data. So these spots are in very particular spots, these numbers, because it's reading it as a full 8-bit number, but we're not really treating it like that. The same with this too. So if the number 0 is red, we want the program counter to jump to 110 because that's where the 0 character data is stored at. As you can see, the 0 character data is right there. So let's say we want to 11, we're going to save 11 and register cell 2. So you can see in a second that it's not going to work, and that's because of the T flip-flop. So once we remove this T flip-flop right here, which is what I'm doing, it will work. So now we're going to print out a new character into the second area of the register, which is X. And then we're going to print out a 0 into the third column. In which it worked. Good, so it works. So now we can, so the GPU now successfully works. So we can now print out data onto our thing. Okay, so this is the final CPU right here, and it's really not that much different than what we did on camera. I did a little bit of work off camera, but we have this instruction decoder, you can say, that's attached to our program counter, and essentially, if the number is greater than 32, we're just going to save the data on the data bus to our GPU, and that's essentially what it is. It's just our little save GPU unit right here, and it's just another decoder that is only activated if it's but above 32. Okay, and then if we go to the big control unit, we have just a few more controls. Again, that goes to the GPU, so we can control the GPU with our CPU. But that's essentially it with our CPU itself. And so we are done with the thing. So now if we go back to our CPU, we hook up our GPU to our CPU, we can create some programs for our CPU to actually run. But first, we're going to add an input signal. So we're going to, into our register cell, the little register cell we made, we're going to use register C as an input register. So that's going to hold all of our input data. And this is going to allow us to actually like talk to our computer with like this little mini keyboard, essentially, this I/O system. Because it would kind of suck if you can only interact with the computer with code, but that will still classify it as a computer. So it wouldn't hurt the definition. So we're going to save this register cell. We're going to go back to our CPU, and we're going to fix the changes that we need to do to it. We're going to fix the wiring first, but the CPU is already looking a little messy. And then we're going to add the I/O input into the CPU just like this. So whenever there's a new I/O data available, we're just going to automatically save it into that register, and then our computer can essentially read that register whenever it wants to see if we did we press a button recently? Is there new data that needs to be stored? So we're going to save this. And then we're going to go, we're going to go make the I/O system. So this is the key button. So this is the key button, and you can bind it to different keys on your keyboard. So when you press that key on your keyboard, on your computer, it sends a high signal out. So we're going to make this as numbers. So when we press these numbers, it's going to send a high signal out into in the program, essentially. And then we're going to hook it up just like this. But I want 1 to be on the bottom, and then 2, and then 3, and then 4, and so on. So we're going to rearrange it in this order like this, just so that 1 corresponds with the least place value, and so on and so on. And if we want to add a lot of keys, we can actually add a decoder to this and decode the data, but we only have 4 keys, so we don't really need it. Because I want to try to keep this simple so we don't have to code that much, because I don't like coding in binary. So this is our inputs module. So now we're going to go onto our computer. We're going to install our inputs module. But we're going to move all of this down first. So this is our memory. So the CPU is still running our previous code, which was just what's 1 plus 0, which is 1. So it looks like it's working pretty well. But now we need this register cell to store data every time there's a button has been pressed. So we're going to make this little module which will let us know, hey, a button's been pressed. You might let's store the data, and that's essentially what we're doing right here in that little register cache cell that we made earlier. So all we're going to do is take OR gates, make it into one signal, and then we're going to process it, and then just hook it up directly to the save pin. So now the save register C in our opcode is obsolete. It no longer does anything. But it seems like it's not working. So what we're going to do is just swap out the OR with a NOR gate, and that should fix our problem. And it does. It will do that, in fact. A little bit of a fast forward thing. So yep, looks like it works good. We can save numbers into our register cell. Good. So now we need a way to reset the cell. So let's say we read the data and we want to reset the cell. So the computer's like, okay, I realize this button's been pressed. Let's reset it so we can wait for new data. We're going to put this XOR gate into it, just like this, and this button right here. So whenever it receives a high signal from the control unit, we're going to reset the inputs register. So we're going to reset the IO, and it works well. So if there's data in it, it looks like it resets. So good. And essentially, we're just going to edit this swap pin. Since we're using a newer GPU, that we don't need this swap pin anymore, and we're going to convert that to reset the IO pin. So now we're going to go back on our CPU, and we're just going to fix these changes real quick. And we're going to delete the swap pin and then hook up this register reset IO pin to where it was. And now it works. So our CPU is 100% complete. So now let's see, we should go back to computer. And if we press the 1 on our keyboard, we should be able to print 1 on our display. And it works. So as soon as we press 1 on our keyboard, we can print the 1 on display as shown right here. So good. So the CPU is complete. Let's run some programs on it. Let's see what we can really do. And you kind of saw the program, the default program I had in it from the beginning, which we're just going to print zeros out in this diagonal line, reset the GPU, and then keep reprinting them out constantly. But that's it for this really episode. So thank you for watching this whole 3-hour video of it. But this computer is pretty good. A few things that maybe we should change is, let's say we want to print a character on our GPU and we want to move that character with our inputs to the left. It's like a video game. So we have to clear the GPU, clear the display out, and then rewrite all the data onto the display. And we can do that with our computer, but that will take a lot of code. So maybe we might need to make a module or more registers so we can kind of store the data for our GPU, and we can kind of like automatically reset the the display. I don't know if you kind of catch what I'm saying, but it would be hard to make characters move around a map with our current GPU setup. But if we had a lot of RAM, we probably could easily do that. But if we have a lot of RAM, that might make our CPU just run at a slower pace. So I did not add the RAM in quite yet, but we could do that. And that's really the only problem that I can think of as of now with our CPU. But thank you so much for watching. As always, if you want this CPU, it's in my shop, which is in the description. But this is how to make a CPU and a GPU, a whole computer, equivalent to 1970s processing power. But thank you for watching.